probabilistic programs. So what do we know quite a bit about termination? First of all, we are all familiar with what is called the halting problem. We are given a program, given an input state S, and we want to know, does a program terminate on that specific input? And we know that this is recursively enumerable, so semi-decidable. If then we look at the universal halting problem, that means, does a program terminate on all possible input states? Then this actually is undecidable. And these are well-known results, amongst others, reported already by Turing in the late 30s. And the question of today is, what happens if we have programs that every now and then roll or flip a coin or roll a die? So some common knowledge that we all have about termination of programs is, first of all, a program either terminates or not, right? So it's a Boolean notion. It's a yes or no answer on a given input. The second issue is that a terminating program has a finite runtime. This almost sounds like a tautology. Of course, in order for a program to terminate, it needs to have a finite runtime. The number of steps it needs until termination is finite. And the third obvious thing that we know about having a finite runtime, that this is compositional. What do I mean by this? If we have a program P, which has a finite runtime, if we have a program Q, which has a finite runtime, then it follows that P followed by Q also has a finite runtime. Why? I mean, that's also something which is rather obvious for ordinary programs. What we're going to see is that all these facts do no longer hold if we have probabilities in programs. So actually, termination is going to have quite a radical change if you consider programs that every now and then flip a coin. And that will be the topic of today's lecture. So first, I would like to explain a bit what termination actually means, and we're going to see different flavors of termination. So the first program, it's a loop program that has only a variable x. It's an integer variable. And what we do in every iteration, we flip a fair coin. This is indicated by this notation. It says with probability 1/2, we will decrement x by 1. And with probability 1/2, we will decrement x by 2. Now, obviously, for any input x, this program is going to terminate. And it's always going to terminate, which means it has no diverging runs. So this we call certain termination. This is the notion of termination we are all familiar with. Then let's look at a notion which is called almost sure termination. So consider the program which is in the middle, where we have a Boolean variable, initially true, and the Boolean variable is used to control the termination of the loop. So as long as the Boolean value is true, we iterate the program. And in the program, we flip a biased coin. And with probability P, we set C to false, which means we're going to terminate the loop. Or with probability 1 minus P, we're going to take another iteration. And for the rest, this program has a counter which counts the number of iterations, which is the counter I. Now, this program does not always terminate, because there is the hypothetical case that infinitely often we flip the coin, and infinitely often we get the option C becomes true, and that means that infinitely often we will take the loop. The probability of this behavior happening is 0, but it is possible. So this program does not always terminate. It diverges with probability 0, because with probability 0, we can infinitely often take this right-hand branch. And what we say is this program almost surely terminates. So this notion is different from the certain termination that we have seen before. This program may terminate, may diverge, but the probability of divergence is actually 0. Good. Then I have an example which does not almost surely terminate. And this is a program that does the following. It's a recursive procedure P, which is defined as follows. We flip a fair coin, and either with probability 1/2 we terminate immediately, or with probability half, we invoke P 3 times in a row, so 3 times in sequence. It turns out that the termination probability of this program is a solution of an equation. If xp is the termination probability of p, then either with probability half we terminate in one step, that corresponds to the skip statement, or with probability half we invoke the program 3 times in a row, and that means actually x to the power 3. And the least solution of this equation turns out to be actually the reciprocal of the golden ratio, the square root of 5 minus 1 divided by 2, and this is less than 1, and therefore this program is not almost surely terminating. Good, so we have seen certain termination, we have seen almost sure termination, and then there is a third notion. And this notion has to do with the number of steps that we need until termination. I illustrate this by means of the example we have seen before. This is this example where we just have a counter, and in every iteration we flip this biased coin. By the way, this computes, of course, the geometric distribution, because the probability that at the end my counter I, let's say, is n, is something of the form 1 minus p to the power n minus 1, because n minus 1 times we take this alternative, and in the last iteration we take this alternative, and that happens with probability p, and that's exactly a geometric distribution. This program, as we have seen before, almost surely terminates, and we also know that the expected number of steps that this program takes is finite, because the expectation of a geometric distribution is finite. What we say is that this program is positive almost surely terminating. It's almost surely terminating, but it does so in finitely many steps on average. Good. Then there is the opposite notion, which is called null almost sure termination. So this program is going to terminate with probability 1, but the expected number of steps until termination is going to be infinite. This is a symmetric one-dimensional walk. We start at some arbitrary position, let's say at position 10. And then what we do, we walk until we hit 0. And in every iteration, we flip a fair coin. So with probability half, we either decrement x by 1 or we increment x by 1. So the way to view that is basically we have a line. You start at some position on that line, let's say here. And then what we do is we want to reach 0. And in every possible step, what you can do, you can either move with probability half 1 position to the right, and with probability 1/2 1 position to the left. This is actually a very well-studied stochastic process, and it's known that with probability 1, eventually we will hit this finish at 0, but the expected number of steps is infinite, because you can walk arbitrarily right to the right, basically. That's the intuition. So this program terminates with probability 1, it diverges only with probability 0, and it has the effect that the expected number of steps until termination is infinite. Now, these notions of termination have been defined in the 90s by Bournet and Garnier. We have seen this notion of certain termination. You always terminate, no divergence. Almost sure termination, there is a possibility of divergence, but this happens with probability 0. And we have seen this can happen in an expected finite number of steps. This is called, in quotes, positive almost sure termination. Or you can almost surely terminate in an expected infinite number of steps, the one-dimensional random walk. And this is what is called null almost sure termination. Good. What I want to show in this talk is actually 3 contributions or 3 results, and I will briefly give some insight into those results. The first issue that we're going to tackle is how hard is it to check these different notions of termination. Then I would like to present you a proof rule to prove that a program is almost surely terminating, and I will give you some examples. And if time permits, I also am going to show you at least a glimpse of a weakest precondition calculus to prove positive almost sure termination. Good. we start with hardness. So we start with part 1. And here the question is, how undecidable is it to check notions like almost sure termination, positive almost sure termination? And then we can distinguish between one input and all possible inputs. And the way we're going to do that is by means of the arithmetic hierarchy, also known as the Kleene-Mostovsky hierarchy, defined by these two famous mathematicians. So let's have a look at this Kleene-Mostovsky hierarchy. So this hierarchy looks as follows. It's indicated on the left. And you have to distinguish between the left and the right side of it. So the sigma side and the pi side. So what does it mean? The sigma pi side means, for instance, that this can be defined by a logical formula that you can write down as a universal quantification and then followed by an existential quantification. So the nesting level is 2. That's what the subscript 2 tells you. And the outermost quantification is a universal quantification that gives rise to the pi. So for instance, pi 3 is for all, existential for all. And on the left-hand side, there is sigma. So this, for instance, means that you start with an existential quantification and then a universal quantification. So what you try to do is you try to characterize the decision problems in terms of statements over decidable relations. And depending on how many quantifiers you need and depending on what is the outermost quantifier, you're on the left or on the right. So a few things you are familiar with. For instance, the halting problem. Does a program halt for one single input? Is recursively enumerable, and that's at the level sigma 1. You're also familiar with this green area in the middle. These are the decidable problems, so all the problems which can be solved in X time, X space, NP complete, etc. And this is another problem you're familiar with. This is the universal halting problem. Why is it in this category? Because you can say for all inputs S, there exists a K such that my program will terminate in K steps. So that gives you the idea why this is on level 2. So you can view this as a kind of landscape of, let's say, hardness of decision problems. Good. So the first issue I would like to attention on is the problem that we consider is almost sure termination for one input. So a probabilistic program, you give it one input and you like to know, does it terminate with probability 1? It turns out that this problem is as hard as ordinary termination for all inputs. So this is here, this problem asked is equally hard as the universal halting problem, the problem for an ordinary program to check whether it terminates for all possible inputs. Good. The second issue that I would like to address is that of positive almost sure termination. So if we're interested in is the expected number of steps until termination finite, then actually if we ask this for a single input, then this is over here. And if we ask this for all possible inputs, this is at level 3. So that means that it's even, let's say, one level more undecidable than the universal halting problem. It's interesting to see that actually here there is this gap between one input and all inputs, which is similar to the gap between one input and all inputs for ordinary programs. And as we have seen, for, let's say, almost sure termination, there is not such a gap between those two problems are belonging to the same hardness class, so to speak. In order to give you a flavor how you can prove these results, I'd like to draw your attention to this reduction. So what we are going to do is we're going to see that past is equally hard as the complement of the universal halting problem. So I would like to give you an idea of the proof. So what are we going to do? We're going to take the following reduction. We give as input an ordinary program Q, and the idea is that we map it to a probabilistic program P plus an input. And of course, this program P may depend on Q. Okay, so we want to have a reduction from the universal halting problem to the past problem. Here is the input Q, which is an ordinary program, no coin flips. And here we get a program with coin flips plus an input state. And the correctness criterion is the following. We would like to have that P terminates in a finite expected number of steps. That means P is positive, almost surely terminating on that input. if and only if Q does not terminate on some input. Good. In order to understand the reduction, I'm first going to explain you how this program P looks like. So let's first start easy, and this is similar to the programs that we have seen before. We have a Boolean variable C that controls the termination of the loop, but rather than my example before, now we flip a fair coin in every iteration. For the rest, we have a counter that counts the number of coin flips, or equally well, the number of iterations. Now, if we look carefully at this program, the expected runtime of this program is exponentially decaying, right? Because the number of iterations is exponentially decaying because of this coin flip. Yeah, so here is a probability 1. Here we have probability half, a quarter, 1/8 exactly, etc. So what do we have? This iteration takes place with probability 1 divided by 2 to the power that number. Now, I hope this is easy to understand, but keep this in mind because this is important for the reduction. So now what I'm going to do is I'm going to use the same structure as here, and now we're going to do that reduction from an ordinary program Q to a probabilistic program P. In order to do that, I'm assuming that the inputs to Q, so the inputs of Q, I can enumerate them. So let's say the inputs of Q are things like 0, 1, 2, 3, etc., so that I can enumerate those possible inputs. And now this is the reduction. So we have given such an enumeration of all the inputs. So this is what I call I, and this can be 0, 1, 2, etc. And now what we do is we use the same scheme as before. So let's make this more explicit. So here again, I have this Boolean C that controls the termination of the loop. And in every iteration, I flip a fair coin. For the rest, I have a counter that counts the number of iterations, which is initially 0, and in every iteration is incremented by 1. So this is exactly the scheme that we have seen on the previous slide. And now what we do is this program P, this probabilistic program, is going to simulate Q. How is it going to do that? Well, first of all, it's going to take an input. We start, of course, with input 0. So that's over here. And now in this line, we simulate Q for one step on input I. So now we run basically program Q. We do one step on input I. And now there are two cases. If Q does not terminate, then we just continue over here. However, if Q terminates, we're going to invoke a special procedure in which we're going to take 2 to the power number of flips effectively steps. So think about this as just a while loop that basically does 2 to the power number of flips times a skip statement. Once we have done this, then actually we have completed input number I, and the next step is going to be that we're going to look at the next input I plus 1. Good. So that's the probabilistic program. So what is this program doing? It's actually simulating Q, but because of the this coin flip that controls the termination of the loop, it's actually losing the interest in simulating Q in every iteration. Yeah, that's the idea. Good. And for the rest, what is critical is this cheering in the middle where we take 2 to the power n number of flips, effectively steps. Good. Why is this reduction correct? In order to show that, we have to consider two cases. The first case, Q does not always hold. The second case will be Q does always hold. So let I be the first input for which Q does not terminate. So how is my program running? Now, remember my red bars, which say something about the runtime of my program. And basically the blue bars are the cheering. Now, why is this exactly also 1? Because this iteration takes place with probability 2 to the power number of flips, right? And how many times do we do the iteration? We do this 2 to the power number of flips times. So this is exactly 1. So that explains why the height of this pillar is exactly 1. Good. Suppose that this is the cheering on the termination of input I minus 1. This is the last input for which Q terminates, because I is the first input for which Q diverges. That means We have finite tiering because we have only finitely many of those blue pillars, and that means the program has a finite expected runtime. Good. That concludes the proof of the first case. The second case, Q terminates on all inputs. Well, if Q terminates on all inputs, we have plenty of those blue pillars because we're going to tier on every termination for every input. Every pillar has height 1, explained just before. So that means infinite tiering, infinite expected runtime, end of the correctness proof of the reduction. So to conclude, what we have is this hardness landscape. It's important to understand that universal positive almost sure termination is at level 3. Almost sure termination is at level 2. Now you may ask all kinds of questions. What happens if I, for instance, allow non-determinism in my program? What happens if I'm not interested in exactly hitting probability 1, but I'm epsilon close to 1? Actually, this does not change the landscape. I mean, the hardness of similar problems in those two places is the same. Good. So now we know a little bit more about, let's say, the level of undecidability of these kind of problems. As a next step, I would like to talk about how to prove almost sure termination. So I'm going to consider actually this case, level 2, and we're going to provide a proof rule to prove almost sure termination. Now, this is an important topic. I don't think I have to spend a lot of words on this. It's often a prerequisite for proving correctness. In many papers on probabilistic programs, this is implicitly assumed. If you simulate programs, you implicitly assume that they terminate with probability 1, because otherwise your simulation might not terminate, and so forth. Good. Why does it turn out to be hard in practice? So this is not a theoretical argument, but more, in quotes, practical argument, because we need a lower bound. And it turns out that proving lower bounds on probabilistic programs is a bit, let's say, in practice, harder than proving upper bounds. And we need for termination probability a lower bound of 1, because that means that we then terminate almost surely. Good. To start off, I like this statement by Esparza et al. In the CAF paper, where he claims that ordinary termination, so termination of, let's say, non-probabilistic programs, is a purely topological property, but almost sure termination is not, and proving this requires arithmetic reasoning. And this is not offered by ordinary off-the-shelf termination provers. So to put it bluntly, we need new technology. We cannot take standard reasoning for termination to prove things like almost sure termination. So let's go one step back. How do you prove termination of an ordinary program? Well, we go back to Turing. What we can do is we use a variant function. What is a variant function? It's a function that maps the program states onto some well-founded domain. And then what we need is a function such that this function, the value of this function, is monotonically decreasing with respect to that ordering. So roughly this looks as follows. So suppose I would like to prove the termination of such a loop, and suppose that this is not probabilistic. Then what we need a function on the states of the program that maps, for instance, states to the non-negative reals. And that works as follows. If we enter the loop, that means if the state satisfies the guard of the loop, then running the body on that state is going to put the value down. That means in state t, the state after the loop, we have that the value is at most v of the starting of the loop minus some constant epsilon. And this epsilon is strictly positive. And because I consider the non-negative reals and this epsilon, this is a well-founded order. If Vs is 0 or at most 0, then actually this indicates termination. So the way to depict this, and I'm going to use that pictures in the future for the explanation later, is the following. So on the x-axis I have the loop iterations, and on the y-axis I have this value of the variant function. So for instance, this means, let's say, the starting state at iteration, at the second iteration, and this is the end state of the second iteration. So this is iteration 2, and this is, for instance, iteration 4. And what we see is that this value, if I compare it to this value, this goes down, and this is at least epsilon. And this is guaranteed to happen in every step, and that means that actually, so here this is made concrete. So this is the value at the start of the fourth state, the fourth iteration, and the other one is the fifth iteration. So we consider this iteration, the value is going down. So this value over here is below that value. And arrival at 0 is guaranteed because there cannot be any infinite chain that goes down. So at some point we hit 0, so to speak. So an example like this is very simple. We just count down, and a variant function, also sometimes called a ranking function, is just, let's say, the value of x, because x is decremented by. Somewhat more involved example, here I have two variables, x and y, initialized with some positive value. And as long as x and y differ, if x is larger than y, then we subtract y from x, and otherwise we subtract x from y. And a variant function that shows the termination of this program is something like the sum of x and y, because you see that this decrements in every iteration. Now, many people have looked at termination of, let's say, rules for almost sure termination. I'm not going into details of these approaches. What I would like to point out is that all share one key ingredient, which is a super or some form of martingale. So let me explain you what is a martingale. So a martingale is, first of all, a stochastic process. Think about this as the starting value at the first iteration. x2 can imagine as the value at the second iteration, and so forth. In my case, in probabilistic programs, this will be random variables, so we have a stochastic process. And such a stochastic process is called a martingale if the expected value of the value of x at point n plus 1, given the entire history, is the same as the value of n. So on expectation, basically, x is not changing in one iteration, if you want. Now, typically what you consider is what is called a super martingale, because now you don't have an equality, but you have an at most, and that means that the expected value of xn plus 1 is at most xn. So that means on expectation, this stochastic process cannot grow. Good, and this is a concept that is used a lot in proof rules for termination. And actually, if you look a bit into history, then actually those martingales and super martingales are used quite a lot. So I would like to mention just briefly a few results on Markov chains. And one is about what is called a property called non-dissipativeness. And this says a countable Markov process, so an infinitely countable Markov chain, if you want, has this property if almost every infinite path eventually enters what is called a positive recurrent state. What is a positive recurrent state? It's a state such that the expected number of steps to go back to that state is finite. And actually, in order to characterize this property, this turns out to be very hard. So people typically define sufficient conditions for this. So one sufficient condition defined by Foster, by the way, you all know this guy because he has been the developer of the ISBN number. This Foster came up with the following constraint. He said, okay, look at the one-step probabilities from states. So he just, the i's and the j's are the states in the Markov process. And then what you have is that this sum is at most I for all states. If this position, if this criterion is true, then it turns out that this Markov process actually is non-dissipative. So he used the state identifiers to get such a sufficient condition. If you go one step further, actually his PhD father, Kendall, that you are all familiar with because he defined notions like the MM1Q, this notation is due to Kendall. He said, well, don't look at the identities, but we're going to define a function. And here you see already this goes in the direction of a variant function that maps states onto, in this case, real numbers. And he changed this condition by saying, okay, if now we have this function, and here we have this function, and it's a very similar condition as for Foster, then actually the process is non-dissipative. And for each positive R, there are finitely many states such that the V of I is at most this R. So this V also needs to be bounded in some sense. Now, this process actually turns out to be a super martingale. And if you go one step further, then actually also there are conditions in terms of Markov chains about when is a Markov chain positive recurrent. So when is the property true that if you are in a given state and you want to go back in that state, you need only expected finitely many steps. Then also there are some conditions, and again, it's not important what these conditions exactly are, but this turns out to be a Lyapunov function. And actually there is a strong relationship between Lyapunov functions and Martingales, also defined actually by this notion by Foster. And here you see very similar this notion that we have seen before for the variant function, that basically you say that this process is basically epsilon going down. Good. So what do we know? Proof rules are based on martingales or super martingales, and there is a lot known already in terms of Markov chains for certain different properties on how to use them to prove these kind of properties. So what is the aim that I would like to show? I don't want to look at the Markov chain of a program. Of course, every program has, let's say, an underlying Markov chain. But I would like to have a proof rule at the source code level. So in particular, I do not want to reason about the underlying probabilistic model such as a Markov chain. And the question is, are we able to achieve such a proof rule? And let's look at our example of before, the symmetric random walk. So this is the scenario up here, is that we have this random walk. We start at some arbitrary position, let's say here, and the question is, can we reach the finish? So one obvious choice could be, we take as variant, as function, simply the position of x. Okay, and then we can say that the expectation of xk plus 1 is actually xk, because if we look at this, this is not going down, but the expected value of x is not changing, right? Because with probability half, we go down with 1, with probability half, we go up with 1. So here we do not have something like xk minus epsilon, because there does not exist such a positive epsilon for which this holds. So we cannot easily adapt, let's say, the standard way in which we define these kind of variant functions. So a naive approach will not work. And actually this example turns out to be out of reach for many proof rules. So what is the intuition now behind the proof rule I'm going to present? Well, what we see from the program, and this literally is almost trivial to see, is that a loop iteration decreases x by 1. So what we see is we have a decrease, let's call this d, and this decrease is by 1. And this is happening with a probability a half. Let's call this p. So p is a half. Yeah. So let's say we have a v, which is the position of x along the line. And then we have two other ingredients, the decrease and the probability. We will see that those two ingredients will become important. And actually, we're going to see that this observation is enough to witness almost sure termination. Good. Before I present my proof rule, I have 3 questions for you. And actually, I hope you are able to solve these questions. So this is a puzzle. The first puzzle is called the escaping spline. You see the picture below. That's probably easy to understand in the program. So it's again an infinite on an infinite line. And what you see is the probability to evolve to the right, so to diverge from the finish, is increasing. But in every step, there is still a possibility to go back. So for instance, at position 4, with probability of 5th, I can go back, and so forth. So here I will have a probability 1/6, and so forth. Yeah? Good. Question, is this almost surely terminated? Good. Think about this. Second example. This is again a random walk, but it's slightly biased, and the bias is a bit to the right. So with a probability half plus epsilon, I go to the right, and with a half minus epsilon, I go to the left. Question, do I reach the finish with probability 1? Yeah. Good. Last one, and also the hardest one. This is a symmetric in the limit random walk. We have seen the symmetric one, where you can move to the right with a half and to the left with a half, is almost surely terminating. And this example over here is actually approaching this in the limit. So here you see with 3/5, I go from position 2 to 3, with 4/7, 5/9. I hope you recognize the pattern. I go to the right. So in the limit, I go indeed with a half to the left and a half to the right. I never reach that limit, but that's the limiting process. Question, does this almost surely terminate? Good. What we are going to see is that this is almost surely terminating, this is almost surely terminating, and this is not almost surely terminating.
Yes, Peter, I'm
Yes.
gonna interrupt. There's a question.
Yeah.
From Jamie Vickery. Don't we need to know the initial value of X?
No. No. I want the question that we're asking is it almost surely terminating for all possible inputs, which means here for all possible initial positions of X. Good. So how are we going to prove this? I told you that we will have 3 ingredients. So we will have a variant function v, which will be a super martingale. We will have a decrease, and we will have a probability. So the variant function is a function that maps states onto non-negative reals. The decrease function takes such a value of v and gives you a positive decrease. And the probability will take such a value and gives you a probability which is strictly larger than 0. So that needs to be the open interval from 0 to 1. These will be my 3 ingredients. Okay, so the martingale is this function I mentioned before. It's a super martingale, which is the property we have seen before. And it means if you run the body on a state satisfying the guard, this does not increase the expected value. And we determine the loop to be terminating if the value reaches 0. Yeah, which is the smallest value in my codomain, the non-negative reals. And then there are these functions p and d. Good. And this is important. We're going to say that the value of v, so the value of the variant function of the martingale, decreases by a certain amount, at least a certain amount. So we only give a lower bound on the decrease with a certain probability, and those probabilities are also a lower bound. In my random walk, I had v is x, p is a half, and d is 1. These were actually exact, but of course also lower bounds. In general, we will have lower bounds. Secondly, in my case here, they were constants, but in general, they are not, and that's important. They are functions depending on my super martingale. That means those d's and p's may change when also my martingale, when also my variant function will change. Good. The last important point is that those functions are antitone. What do I mean by this? Well, if x is at most y, then f of x is at most f of y is of course what is called monotone. So what is antitone? If x is at most y, then f of y is at most f of x. This is what we call antitone. Yeah. So it's monotone but going down. Good. We're going to see if those ingredients are there. So if v and p and d satisfy these preconditions, then the theorem says the program is universally almost surely terminating. So regardless of the input state in which the loop will start, the program will terminate with probability 1. Good. Let me explain the intuition behind this rule. So again, same picture as before. Variant function on the y-axis, the loop iterations on the x-axis. Let's consider this iteration over here. So we start with v1, and this is the beginning of the iteration, this is the end of the iteration. Good. What do we know? We know that this v goes down with at least some decrease, but it is important that this decrease depends on this value. So this thing is exactly this value. So depending on the value of the variant in which you start the loop iteration, you will have a lower bound on the decrease. And in addition, this decrease will happen with a probability, which is a lower bound, and that lower bound depends on this point. Good. So that's what we know. Now let's look at an iteration a little bit further on. So we just have seen now this iteration here in the beginning, over here. Now I'm going to look at this iteration, which is a little bit further on. Same kind of reasoning. We have an initial value where this loop will start. Let's take this color for the initial value. Then this is going down with a bit. What is the value? Well, the lower bound is d of this value, and this happens with a probability which is at least p of that value. Good. Okay, I hope that you understand what happens in every iteration and what are the, let's say, the requirements for this. And now the antitone aspect of the two functions comes into play. Remember that these functions are antitone. What does that mean? Compare this value to this value. And what it means is, because the function is antitone, it means that we have this relationship. It means that this value here is actually at least the value that we have here. So the lower bound on the decrease is increasing while we look at loop iterations further on. In addition, because the probability function is also antitone, it means that this probability and this probability, if we compare that this probability is at least the other one. So we have that the P of V1 is at least P of V4, because that's antitone. So intuitively, what happens? The decrease is increasing when moving in that direction, and the lower bound on the probability that this happens is also increasing when moving to the right. So actually, the theorem now says that almost surely you will hit 0. So it's not by a kind of well-founded argument, it's basically because of the proof rule and the proof of the proof rule that says this.
Joost-Pieter,
yeah.
Sorry. I just want to signal that you're a few minutes from the time.
So to put it in one line, the proof rule says the closer to termination, the more V decreases and this becomes more likely. That's what the proof rule says. So let's look at the symmetric random walk example we had before. How to prove termination? V is x, P is a half, a constant, and D is 1, because we see from the code directly that in every iteration, with probability half, at least with probability half, we will decrease with at least 1. And it's easy to check that these three things fulfill all the constraints of the proof rule, and that ends the termination proof. So this is all we need to prove termination. The escaping spline, this program where the probability to move to the right is increasing, can also be shown to be almost surely terminating. And this is the witness we need for this. Again, we take the position along the line. D is the constant, because that's 1, because we decrease in every iteration at least 1. Why do we get this 1? Well, basically, this comes from this jump over here, where we can only go 1 position to the left. And the probability that this happens is 1 divided by 4 plus 4, this value, and that's exactly the probability which is on those back edges. And similarly, you can prove things like the symmetric and the limit random walk, like this, where actually now the function V is a bit more difficult. It's a harmonic number. So it's the x harmonic number. It's no longer suffices to look at the position along the line. The probability now turns out to be constant. This comes from this 1/3 over there. And the decrease is now a function depending on x. The decrease is basically 1 over x if basically this lies, if for every v which lies between two harmonic numbers. Good. How many minutes do I have left, Alexandra?
Basically 1 minute.
1 minute. Good. The last thing I want to show you is that we developed also a calculus to provide to prove positive almost sure terminating. And the only thing I would like to show you is the following effect. I can make the slides available for those people that are familiar, that are interested. So the important point is that positive almost sure termination is not compositional. And I show you by this example, and then we stop. So this example is similar in Wien as the examples we have seen before. We have this Boolean C controls the termination of the loop. And for the rest, we have a variable x, but now x is doubled in every iteration. But for the termination of the loop, right, it doesn't matter what we do with x. So the termination, of course, is still a finite expected termination time. It's still modeling a geometric distribution, now with probability half. So this program is definitely passed. Now let's look at the second program, which is the program on the right. That program also is definitely passed, because we do not even flip a coin. The only thing that this program does, it counts down. Good. And now consider the sequential composition of these two programs. So here we have a program which was passed. Here we have a program that is passed. And if we compose them in sequence, we get a program which is no longer positive, almost surely terminating. And why is this? Well, what you see is that in this program, of course, the termination time depends on the initial value of x, right? It's a linear decrease, it's a linear function in the initial value of x. Now, the point now is important that in this program, basically we duplicate x in every iteration. And that means actually that the expected value of x on termination of the left program is infinite. Because in principle, what you get a sum that with probability 1 divided by 2 to the power x, we have a value which is 2 to the power x, and that actually turns out to be infinite. So the expected value of x after termination of the first program is infinite, and therefore on the expected number of counting down steps of the right program is also infinite. What have we developed to prove such a thing? We developed a weakest precondition calculus, much in the same vein as Cozen and McIver and Morgan, to determine expected runtimes of these kind of programs. And this can be used to also prove positive, almost sure termination. So I like to conclude by saying that we have seen something about hardness of probabilistic termination. I think two things are important. The problem for one input, proving that it terminates with probability 1, is as hard as proving termination of all inputs for ordinary programs. And positive almost sure termination is actually even one level up. It was at level 3. We have seen a proof rule for almost sure termination, which actually is relatively widely applicable. And I did not present you this in detail, but we have a weakest precondition calculus to compute the expected runtime, and this can be used to prove positive almost sure termination, but also other things. Good. Let me conclude by thanking my co-authors, because without their contributions, I would not be able to present this work. So a big thanks to them. And if you are interested in further reading, here are some publications. But I also advise you, if you're interested in termination, to read this upcoming chapter in an upcoming book, which actually is a very nice summary on termination proofs, and also talks about automation, which I did not talk about. But there is work on termination analysis in an automated way, and in that chapter they summarize what's the current status there. Thank you for your attention. Thank you.
Okay, thanks, Joost-Pieter. I'm going to unmute everyone so that we can clap for Joost-Pieter. Okay. So now we're going to take some questions. If you want to ask a question, can you please use the raise hand feature on the chat so that I know whom to unmute. Let me see. And in the meantime, while I'm figuring out who wants to ask questions. Okay, here's one question. Paul Levy, go ahead.
Hello, can you see me or hear me?
Yeah, we can hear you.
Okay, right. Just quick question. By program, do you mean like program just like your programming language is while loops with finitely many global integer variables? Is that kind of what you, I mean, that was what you had in your example, so I wondered if that was exactly what you meant by program.
Exactly. So we talk about sequential programs. Think about variables which are integer valued. We just have while programs and that's it. Yeah.
Okay, thanks.
Okay, we have another question from Jamie.
Hi, Joost-Pieter. Thanks for a very nice talk. You said about halfway through, ordinary termination is a topological property. Could you say a bit more about what that means?
Well, that was a statement that I quoted from a paper by Esparza. And I think what he meant is that basically, if you look at the control flow graph of a program, that he's arguing that based on the topology of these control flow graphs, you can already say something about the termination.
I see. Thank you.
So it's a kind of, what he's arguing is a kind of a graph theoretical question. You don't need arithmetic reasoning, whereas, and that was the, let's say, the opposite with probabilistic programs, there you need also arithmetic reasoning. Mm-hmm. That's at least the way I interpret his statement. Yeah.
Okay, thank you.
Okay, there will be more opportunity to ask questions to Joost-Pieter during the break. People who want to stay, who do not want to stay for the break, should log out now, because I'm going to divide everyone who's left in 1 minute into breakout rooms, and then I'll be moving people into Joost-Pieter's room as the number decreases. So if you're not interested in the break, you should log out now.